So we have a couple different models for allostery. To develop a model that captures cooperativity, we have a couple assumptions. So like I said, for allostery 1, we're going to let the protein be in a ligament with different subunits, and each subunit will be binding each one of these ligands, okay, in this allosteric cooperative sort of combo scenario. Each subunit can only exist in 2 states, okay? The T state or the tent state. This is the state that dominates when there's no ligand attached. And then also what we call the R state or the relaxed state. This state could have a ligand attached or not, depending, but it is a state that has a higher affinity for the ligand to bind. So once you turn into this state, your affinity goes up for your ligand. T state has the lower affinity for the ligand. And then you're also going to assume all the binding sites are equivalent. They have identical binding constants for the ligand. The Monod-Wyman-Changeux model, or MWC model. It's also called the concerted model because what we're going to do is assume that the switch from T state to R state happens all at the same time. Okay? So T state here is a square, and R state is a circle. And that's the same on the next model we look at, and it is different on the final model we look at where they switch them. So just, you know, whatever. Here we have our empty state. T state is empty. Maybe don't bank on square versus circle. So here we have hemoglobin. All of our subunits are in the T state, the empty state. There's no ligand attached. The preference would actually be from, you know, just one oxygen binding to having no oxygen bound. Actually, probably prefer to stay in this state since getting that first oxygen to bind is a little bit more of an energetic barrier. But once the first oxygen binds, there's a conformational change. And again, with this particular concerted model, all of them are turning to the relaxed state at the same time after the binding of the first oxygen. And then we know that the affinity for each additional oxygen is going up. Okay? And it makes it easier for the next one to bind, the next one to bind, and the next one to bind. Okay? So let's think about this model for just a dimer, okay? Two states, or I'm sorry, 2 subunits. Okay? So here we have at a very low ligand concentration, okay? If ligand concentration was very low, not very much stuff is actually bound. Your protein here, which now is a dimer and has 2 subunits that can bind the ligand, each one can bind 1. It's mostly all in the T state. As you raise the concentration to some sort of intermediate state, you'll have some intermediate concentration. You will have some of them bound. Once they bind, both sides are going to turn into the R state, okay, under our concerted model. And then at very high concentrations, you would expect almost everything to be bound, and then thus everything is in sort of the R state conformation. So recall for a binding isotherm, we can plot ligand concentration as we raise ligand concentration against fractional saturation, so the number of proteins that are bound. Okay. We can use some log axes to make it a little bit easier for us to understand and read the actual KD value when we're having switches in a really small range. So now that we have an understanding of why things are able physiologically to switch in a really small range, again, why is this a situation that actually happens? Because real-life systems are what type of systems? What was the word for the rapid, narrower switch over a smaller concentration range? Ultra-sensitive, okay? Physiological systems are generally ultra-sensitive systems. We're not really changing over 100-fold concentration, which is why we cannot discern it. Where's my mouse? Okay? So we use log axes so that we can actually get KD. In our log-log plot, we have log of concentration versus the log of the fraction bound over 1 minus the fraction bound. So of course, KD is equal to our ligand concentration when fractional saturation is half, which means that this would be 0.5 over 0.5. The log of 1 would be 0. So this is how we pick where our KD value is. It'll be where this is crossing the 0 point, and then we could get log of KD, and we could get KD. So here what we have, we're going to assume we could draw 2 of these curves. Okay? We could draw one for the T state, if everything is in the T state. And we can draw one curve if everything is in the R state. Okay? So the T state is the blue line, and it has a bigger KD, right? Because it is lower affinity. T state is sort of the lower affinity, doesn't want to bind as easily. Once it binds, we're in the R state, which has higher affinity conformation. So we expect between T state and R state, KD would drop. Okay? So now KD is lower. There's sort of this shift in the left to this curve. So the left plot shows the expected limits. If you have a dimeric or a 2 subunit protein that's showing positive cooperativity, and the green curve on the right is showing actually the fact that when you fit this model, there's going to be a switch between the two. Okay? Where you're sort of going, everything is in T state. As you raise the ligand concentration, you're seeing an increasing number of things switching to R state. And so eventually then everything would be in R state. And so this is a way to see how your binding isotherm changes.